Okay, so welcome everybody in the first semester of quantum information and first meeting of quantum information and quantum computing seminar this semester. We are starting with a talk by Daiki Suruga, who is a postdoc in my group, who joined in June. So if you haven't met him, so this is Daiki.
I see.
Yeah, Daiki is a computer scientist who did PhD in University in Nagoya with Francois Regal. Right, and today he'll be talking about estimation and learning of functions of unitaries. So great to have you, Daiki.
Yep.
The floor is yours.
Okay, thank you for the introduction. So I'm gonna give a talk with this title, and of course I will welcome any kind of comments or questions, by raising your hands or like making some noise. But be sure that I'm not a physicist, so I don't understand some of your questions. Like some technical photons or whatever. So, but please try to ask me anytime. Yep. Let's just start with a brief introduction of me. And I'm currently a postdoc here, of course, and I'm originally from Japan. And my interest includes like computational complexity stuff, like the complexity class P is not equal to NP stuff, and the communication complexity, the number of qubits or bits required to compute some function between Alice and Bob stuff, or more broadly, quantum computation, information, and information theory, and etc. So I also want to mention again that my expertise does not include some specific Hamiltonians, boson fermions, CFTs. I guess Miha would have understand well how much I am so bad at these kind of topics.
That's not include yet.
Yeah. Yeah. Exactly. Yeah. But anyway, I welcome any kind of comments from all of you, any of you. Yep. So this is the cat in my Japan. I like cats and dogs. Anyway, so let's start with some overview of my talk, and this includes some background and simplified statement of the result. And after that, I'd like to present some detailed exposition and formal setup of our result and statement formally, and the procedures will follow. Lastly, summary. And I guess the talk will be finished in 40 or 30 minutes. So after that, if I have time, I'd like to explain briefly about what I've been doing recently, or just some of my earlier works. Okay, let's start with overview first. So the inevitable truth is that we want to estimate unitary operators. So you must all agree the importance of estimation of unitary operators. I guess so. You agree? Okay. So
estimation of a unitary operator mean?
So So I'm gonna explain briefly from here. So by the law of quantum mechanics, so any kind of closed evolution is described by some unitaries. Yeah. It is one of the most fundamental laws of quantum mechanics. And therefore, many tasks in quantum information science involve some unknown unitaries, like verification of quantum circuits, or to understand hidden dynamics, or we have to sometimes evaluate underlying unknown noise, which can be coherent, etc. So in such cases, we have to estimate the underlying unknown unitary operators. So does it make sense to say, Oliver? Okay, fairly.
Sure.
Okay. So one main question, and the research have been focusing on, is how do you estimate unitary operators? There are several good ways to estimate them. So one way to do that is full unitary tomography. So of course, if we can estimate all of the matrix elements of unitary, so we can of course estimate any of the properties of unitary operator have. but this costs approximately dimension squared number of samples to unitary. So it is exponential in qubits and therefore inefficient. Yeah. So that is one caveat of the full unitary tomography. Instead, in my work, we focus on the estimation of some function. Yeah. So here, instead of estimating the whole unitary, but some specific function like trace u or determinant u. In this case, sometimes for some specific functions, we do not need exponential number of samples, so we can do it efficiently. Yeah. And yeah, in particular, some specific function only need constant number of samples to access to u unitary u. So now let's look at some good examples of this, number two. Okay. So one good example is Hadamard test. Hadamard test is described in circuit in this way. And the Hadamard test, if we start with the state, the initial state is 0 tensor psi, then the difference of the probability here becomes the real part of this value in the product. And if we instead start with another state, the difference of the probability becomes the imaginary part of this one. And therefore, we have a good estimator for unbiased estimator, say, for this inner product. And of course, you can see that we only use one query, one samples to control the unitary operation here. So the good point of this Hadamard test is we only need to use constant queries to control the unitary, and which is independent of the system size, right? No matter how much the space becomes larger space, the unitary lies, we only need constant number of samples. But bad point of possible bad points of the Hadamard test are we can usually this only works originally for the value, the inner product, and it has some limited applications like the normalized trace described here. Here, of course, we can estimate with the probability 1/d. We estimate this value via Hadamard test. Yeah. So it has several applications other than this, but yeah, the number of applications are not so much. So researchers have discovered efficient estimator, including Hadamard test, using the Hadamard test, like for the trace function, determinants, and other eigenvalues, properties, and so on. So what is missing here is that we focus on in this talk is that unified framework that works for arbitrary function f. So for any f, we create we have some procedure that creates some estimation method, efficient estimation method applicable for the chosen function f. We'd like to create a unified framework for that construction. And our contribution includes some optimal estimation for any kind of f, but under one criterion. Yep, under one criterion, which is not the standard stuff. So this is my possible bad points of the first result. And in the second contribution, we have created the generalized version of Hadamard test, and which becomes optimal in many cases under PAC criterion. So PAC criterion is a very standard criterion in estimation theory, or any kind of tomography stuff. And based on these two results, we made some applications which include the optimal estimation of trace or determinant or representation theoretic functions. So is there any question or comment here? This is a very simple overview, I guess. Any comments are welcome anytime.
how are these functions important in quantum information processing?
Oh,
Yes, and determinant.
I don't know. Yeah, of course, it is sometimes important because trace and determinant have many good properties like cyclicity, or determinant has of course it is characterized with some mathematical properties. So yeah, when we want such properties, we have to use trace or determinant appropriately. But I cannot say here now any kind of good example why the trace or determinant is important.
Okay.
Yeah, for some cases. Do you have any?
I have
idea?
a comment. This could be wildly wrong, but my feeling is always I'm kind of always suspicious of anything which is a function on the unitary group, but not on the projective unitary group, right? Because in quantum physics, we usually don't care about phases on our states.
Yep.
So
yeah,
determinant is super dependent on your phase.
yes.
Yeah.
I'm gonna explain that later.
Okay.
Yeah, good comment. Thank you.
But I think like in some cases like this Hadamard test is like can be, it's like BQP complete if I remember.
Yeah.
Right. That's so estimating trace of it, but what's the okay, I cannot recall what's the hardness of estimating trace, for example, computational hardness. Do you remember? Like it's probably
It needs some assumption, of course. So, but it is almost like DQC1 optimal.
I see.
Yeah, as far as I.
Right. So something that people just putting out like maybe not like something that people care maybe is like they sometimes don't take functions of U, but they can take functions of Hamiltonian. And just like yesterday with Marcin, we attended some nice talk by Yuri Quack, and like sort of for Hamiltonians, like so they doing functional calculus can be useful, just comment. So perhaps here it would be useful at some point.
Yeah, I hope so. Yeah, somebody finds very good applications for our works. So yeah, so let's take a closer look at our contributions. Detailed positions cards. So we now formally set up my query model. So we focus on the query model that have access only to controlled unitary operation, not direct original unitary. Yeah, so here any kind of direct unitary, original unitary, or the inverse of controlled unitary is not allowed here. And one note is that initial states and each VIs here, after applying some controlled unitary, we apply some unitary V1 and V2 so on, but they are arbitrary. So we do not focus on any hardness. It can be computationally hard to create, but we do not care here. Yeah, and the goal is of course to understand how many controlled unitaries are required for estimating function f. So one questions, so related to Oliver's comment is why not access to unitary solve? So it is simply because U alone, the unitary, original unitary alone is insufficient because it has some phase ambiguity, global phase up to global phase, unitary is characterized. And another way to deal with this is consider some projective unitary group. It is smaller than original unitary group, but we do not discuss here in this work. But instead, we want to work with any kind of function over unitary. So we have to use controlled unitary. But so nevertheless, one thing I'd like to tell you is that our lower bounds hold with stronger query model that have access to unitary or controlled unitary or the conjugate, in the inverse of unitary, etc. So even we can use these three or other operators, we can still show the same lower bound of the number of samples required for estimate any error. So the second thing I'd like to tell you is the accuracy criteria. So we have some accuracy criteria And one criterion I'd like to use is that the average bias over the Howell measure, which is used for my first result. And for an estimator is always described in this way. So we have, after applying some unitaries, we measure and get some outcome. And depending on some outcome, we provide some complex numbers. This map is called estimator. And that bias at U for any, for at a U, unitary U is defined in this way, which is just the distance between the optimal accurate true value and the expectation of the estimator. Yeah, it is a natural definition of bias, and if it is 0 for any U, it is called unbiased. So the average bias is the average, the expectation of the bias of the unitary group, when the unitary is distributed according to the Howell measure. So this is the definition of the average bias, which is used for my first result. And of course, if we want to make this value smaller, so smaller bias is better. So we'd like to understand how much, if we want to make this small, how much samples are required. We'd like to answer that question. Okay. The second one is based on probably approximately correct criterion, so which is abbreviated to PAS, and this is used for the second result. The criterion is very simple for any unitary. The distance between the true value and the output, the outcome of the estimator has to be smaller with high probability. And of course, the second criterion is more strict. This means average bias criterion is easier to satisfy.
So this probability is over output for fixed U.
Yeah.
Okay.
Yep. So we now explore the first and second results separately. The first result says for any function f, so which is any element of the square integral functions on the unitary group U, and L2U includes continuous functions as an example. So this is a very large class of functions. And for any f, the quantity, the degree of f characterizes the sample complexity, the number of samples required for estimating f under the average bias criterion we have described already in the previous slide. So this is one of the results, but we have not defined degree of f yet, so I would like to explore later. And the second result is based on the first result. We have created some algorithm that works for estimating any polynomial in the matrix element of unitaries. And under the PAC criterion, more standard criterion. But works only for estimating polynomial. Those are the two main results of my work. So, do you have any comments here? No? Please feel free.
Sorry, can you repeat again what's the meaning of the second result?
The second result is the existence of a nice algorithm, estimation algorithm, that works for any polynomial in the matrix element of unitary.
Okay, as of like, and the probably like difficulty of this algorithm, like, or how, complexity depends on degree probably of the polynomial.
Yeah. So the second result will be discussed more formally later. But first, let's look at the first result.
Wait,
Yep.
So for the second result, the matrix is exponentially big, right? So this,
Sorry?
the matrix is exponentially big, 2 to the d by 2 to, 2 to the f by 2 to the n.
Yep.
So the polynomial is also exponentially big, right? This is
But yeah, for a randomly chosen polynomial will have exponential degree. But yeah, we can of course say in case of choice of unit u, the choice of unitary is only the the 1 degree, because u11 plus u22 plus and so on, and all has the no power. Yeah. So yeah, u11 squared may not appear here. So it is 1 degree.
okay.
Yep. So yeah, I'm gonna explain it anyway, and you can ask me anytime. So the first result, yeah, we have proved this is that for any function, we define intuitively the degree of f as the minimum degree of polynomial that epsilon approximates f. So yeah, g here, g epsilon approximates f. And then yeah, we have, having defined degree f as this, we can claim the following two. One is that approximately up to constant, meaning up to constant factor degree of f samples are necessary to estimate f. On the other hand, there is some estimation algorithm, estimation procedure using only the degree of f samples up to constant factor to estimate f. So, yep.
But to estimate f to accuracy epsilon or
accuracy, yep. So accuracy, yeah, average bias has to be less than it.
Okay.
Thank you.
Okay, I see.
So this is for the lower bound, and this is for the upper bound of number of samples. So we have, we can now say that degree of f samples are necessary and sufficient up to constant factor. Okay, so yep. So intuitively, degree f is defined precisely in this way, but it's not formal. So I'm going to explain a bit about formally how to define the degree of f with subscript epsilon, yeah, in the next slide. But it's not so important, so you don't need to pretty much focus on what I've been saying from here, yeah, in this slide. So intuitively, degree is defined in this way, but more formally, for any f and for any integer, positive integer m, we decompose f into some polynomial part and the rest, so that this satisfies these conditions, and if this polynomial with degree less than 2m has the smallest, this one. So we want to we want to have some polynomial with degree 2m that optimally approximates f. This is the definition of f less than 2m. This is the definition, and which is ensured. The existence is ensured by the Peter-Weyl theorem from a representation theory.
So what can you say again? So like the second condition is that this orthogonal polynomial has the smallest norm.
Yeah,
this can be 0, right?
The rest is the rest has smallest norm. Yeah,
can be 0, right?
It can be 0, of course. If f itself is a polynomial. If f itself is polynomial, then we can just express.
So both f is more equal to m and the other one are polynomials? No, the other one is not.
The other one is not.
Okay.
The other one is just f minus f less than 2m.
It's just the projector right onto the subspace. So
yep. Yeah, we can say there is we have some projector that project onto the space of polynomial here, actually, which is ensured again by the Peter-Weyl theorem.
So can I ask, like, why it's up? You have degree 2m, not m?
Oh, it's a very technical reason, then. So I can use m instead, of course, but then we cannot say the lower bound is exactly equals to degree of it. So I will explain later that the lower bound matches exactly degree of f.
Mhm.
But if we do not attach 2 here, the lower bound is like 2 degree f, 2 multiple
Okay.
degree f. So I have attached 2. So
you change the definition.
yeah.
Okay.
Yeah.
Okay, because like if you had projective unitary group, you would have balanced polynomials,
Mhm.
right? So and it's like natural that they have like even degree, but here you.
Oh, okay. Yeah. We do not have such a summation. And I'd like to explain a bit more about the degree here. So degree, a polynomial means, of course, as I said, as the matrix elements of unitaries. But in my paper, it is also allowed to use the conjugate of the matrix element. And yeah, of course, this can be polynomial in the matrix element of unitary or its conjugation. And this, of course, has degree 2 equals 2 in this example. So this is the meaning of degree here. So as m goes large, of course, we can estimate a lot of part of the original f. So the norm of the rest must go smaller. And we have defined degree f to be the smallest m that attains the value goes less than epsilon. This is the formal definition of it. Yep. But yeah, anyway, you can forget this. It's not so technically important for my talk. Yep. So yeah, we have now formally defined what degree f is. So let's start with the understanding claim 1. Yep. And this is the claim and proof idea is that for the final state of any sample estimation with using m samples to control unitary, the state is described in this way. And because this is just a matrix multiplication, and each element of this vector is m degree polynomial in U. And therefore, the probability of getting some outcome, specific outcome, each outcome at some unitary U, and its expectation is also m degree, but it becomes 2m degree because it's square up here. It has to be squared to get some value probability. So these are 2m degree polynomials in U. And if we have to satisfy, we want to satisfy the average bias is less than epsilon, we need to satisfy this expectation approximates f. Yeah, epsilon approximates. Therefore, we have the degree is larger than m must be larger than degree of f, or at least equals to. This is a proof idea for the claim 1. Do you have any comments or question at this point?
Yeah, so just the idea is just this estimator is itself a degree m polynomial. Yep. So the bias would be what's like lower bounded by this approximation used in the definition.
Yep, right. This is the proof sketch of the first ring. And this, what is this? Okay. So now let's move on to the proof idea for claim 2. So in claim 2, we want to create some estimation algorithm that uses the factor degree f sample. Proof idea is that for any polynomial P, we create some estimation algorithm that is unbiased. For any unitary U, it has to be 0. The bias has to be 0. And it only uses 2m samples for m degree polynomial. This is how we like to create, what we'd like to create. And after that, so for any f, we decompose f into that one part and the second part as we have done for defining degree. And we just focus on the estimation of this part, less than 2m part. Then, because of the existence of the estimation algorithm, we have the estimator for p hat, and this satisfies because we can correctly estimate this part. What we cannot estimate is this part, so it has a norm less than epsilon. Yep, when degree is larger than m, because the definition of degree, we must have the norm less than epsilon. Yeah. So this is the proof idea, but we now focus on how the estimation algorithm is made. Yep. Do you have any comments here for that? Okay.
So we're gonna now, and this estimation algorithm would be also for the use in the second result.
Yep. Yeah, right. So this is the second claim, and after that, I'm gonna explain the second result.
Yeah, but like it's sort of like second result fits in here because like the claim is you can have unbiased estimation.
Sure.
For
Sure.
for functions that are finite degree polynomials. Okay.
The second result focus on that one. Okay. So this implies that the 2 multiplied by degree f samples suffice. So we can prove this one. We have proved. Okay. So the only problem is that the existence of estimation algorithm. So I'd like to explain now. Let's discover this. Okay. What we want to have is this algorithm. The idea is just to generalize the Adamar test in this way. So yeah, very generalization from the Adamar test, but it has some certain similar structure. It starts with H, and the initial state of one part is 0, and you end up with the head of gate, and finally measure 1 qubit here. Yep. So this is the generalized Hadamard test.
Sorry, I got lost for a second. So what are those C's again?
C's are defined in here.
Okay.
Yeah, and it uses one controlled-unitary operation.
Okay, and what's H?
H is just Hadamard gate. So
okay, but H in the definition of CN.
Here
It's also Hadamard.
here is the register here.
Okay, the Hadamard register.
Yeah.
Fine.
For the Hadamard register.
And A and B
is okay. So yeah, it is just one part of the register.
I see. I see.
Yeah. So we have A1 to AM that consists A. So
Okay, but like those C's, they act on H, A, and B registers, if I understood.
yes,
Well,
AN acts on H, AN, and BN, and the A and BN are subspace of the AM.
I see. So you just pick you pick pairs, let's say. Oh.
Yep.
And
There is also this U phi and U psi. What
yes.
is it?
Yep. It also appears. So yeah. I guess it's time to introduce. Yeah. So for any psi and phi, so unitary is for the generation creating the two states. So from the initial state, it produces psi, phi, and it produces phi. This is the definition of the unitary.
So I have just like high level question because like I remember when you were working on those results some months ago, you were using Schur transform,
Yeah.
right? So so you sort of decided to go away from it and you use this instead, or maybe it's yeah.
Yeah, actually, so the Schur transform is one important application of my result.
Okay.
Yeah, we select yeah, so we select so Schur transform will be for some examples or subsumed in the definitional state. We use some Schur transform unitaries, yeah, to get some state. Yeah, and we have some example for estimating matrix elements of irreducible representation, unitary group representation.
Okay, I just want to, yeah, just
Sure.
I want to understand something here, like, because if I have just this, because like the idea of this test is to estimate this, say, overlap, right, between states, right?
Yep.
Like, so, sorry, like this matrix element, right? So why one cannot just use a Hadamard test, but like applied to bigger, let's say for simplified case when I have where psi equals to phi. Why I cannot just use simplified Hadamard test, but now instead of a single unitary, I'm just gonna stack together U and U star, because I have access to U star, don't I? In your query model, or you don't have?
No.
When you see you.
Ah, but you have you controlled.
Yep.
Okay, so here's another question.
Yep.
If I have access to you and you controlled, do I get access to U star?
No.
Like I cannot compile perhaps from you and
Control to you.
let's say I have access to you.
And control to you.
Yes.
It's not that obvious to me.
Okay.
But yeah, I don't know.
I see. And okay, that's why I guess you okay, that's why you had access. Because I think that might be okay. That might suggest that you can do it, right? Like if you have that you could have because there are different query models. Some of them like allow you to have inverses as well, right? And perhaps one could, yeah. Yeah, one would craft such like from couple of queries like this, you get access to your star, and then you just go with Hadamard test. But okay, this is just comment.
Yeah, comment. Yeah, good comment. Thank you. Yeah, so
I'd like to understand this. So you claim that there, for an M-degree polynomial, there exists some algorithm, and this algorithm is this quantum circuit. Yes?
not itself.
It's not?
Not itself. This is just provide unbiased estimate for this part.
Okay.
So, yeah, in the next slide, I'm going to give the exact algorithm.
Okay, then I will have another question.
Okay, please. So yeah, so let's use this, the general Hadamard test for estimation of. Yep.
What is that the zero state going to this?
What is it, zero state?
No, like at the bottom.
Oh, here?
Yeah.
So it starts with 0 and end up with 0.
It's a kind of ancilla, but
Yep. It's the answer.
how is the part of this this whole psi when we compare to the Hadamard test?
So what is your question?
It's just a generalization of Hadamard test, right?
Yeah, originally Hadamard test does not include any kind of answer.
Yeah, so if we map 1 to 1, like 0 is the first qubit, and then this whole initial A, B, C, D, E, and the 0 state is kind of psi, right?
Yeah, it can be 0 anyway, but yeah, just independent of any kind of stuff. So depending on this value only depends on the definition of U phi and the U psi. Yeah.
Right. So maybe just like this. What are those U psis and U phis?
For just any person.
Yeah, but how they are defined?
On the space of the ABCD.
Yeah, but like how like
It's anything that produces phi and psi from a zero state, right? I think it just prepares. They just prepare phi and psi.
okay.
Do you want to know the definition of the states, right?
Yeah, I mean, so you have states, but then in the diagram you don't have states, but
Yeah.
you have unitaries.
So instead we have.
Yeah. So what are those? How they are defined?
This is defined as the changing initial state to phi, yeah,
Interesting.
yeah, and changing the initial state into psi.
Okay, so then I have
Another question.
okay, I see. So you okay, and you just sort of you have classical description of this psi and phi, so you can do it. Okay, good.
Yeah.
Good. And you have controlled version, so fine.
Okay, thank you.
Okay. So let's start talking about the construction of the algorithm we want. So for any state, we have the unbiased estimator for this value. And one good observation for estimating polynomial is that any kind of polynomial with m degree may be expressed by this one, the trace of the one matrix P and the tensor of some tensors. Yep, for some good matrix P. This is one observation. It can be a bit not so simple at once, but yeah, you can eventually understand. It's not so difficult of observation. Yeah. So, for example, unitary is U11, U22, U21, U12, and we want to have U11 plus U21, say, and which is the trace of U11, U2, U12, U22, and this should be, I don't know, 1, 0. I'm not sure. I don't know.
I think 1 0, 1 0, 1 0.
One, yeah, 1 0 may produce
Something
this.
like this, yeah.
Yeah, this is just because this is just you know, it produces some inner product as a vectors. So we can eventually get for any unitary, we get some good metrics here that we can express any polynomial. This is the observation. Okay, then we decompose P by the singular value decomposition and they get this expression for the polynomial U. And therefore, we estimate each of this red with probability sigma 1 over the norm of P, which is just the sum of the singular values. This is the definition of one norm of the matrix, and becomes unbiased for the polynomial. So this is the algorithm that we want to have. Yeah. So we can now get polynomial unbiased estimation for the any kind of polynomial with with 2 and sample. So as I have described already, because we have now the estimation algorithm, and the rest follows. Yeah, as I have already described, it ends the proof of the second claim. And we have now shown that the claim 1, the first result. And you have a here? Okay.
I mean, just a comment, because like you could have just get around with without having psi and phi, you would just in this generalized Hadamard tests, right? You could just sort of, like every P can be described as, you can maybe, because you don't want real polynomials, you want arbitrary.
Yeah, with complex values, maybe.
Okay, okay, so it's going to be sure.
But
I guess like probably one can get around with situation psi equals to phi and just having big linear combinations of all of them. That would just work, right?
for
I guess.
any real polynomials in that case.
For I am maybe for any, but just maybe like a bit more. Just would maybe trace complexity of like maybe this test would be a bit less, would have fewer parameters, but then you will have bigger linear combination. Yeah. Okay.
Okay, thank you. Okay. So let's move on to explain the second result. Yep. In the second result, formally speaking, what we have done is that for any m-degree polynomial, there exists an algorithm that estimates the polynomial with this number of samples and the PAC criterion, where this P satisfies the matrix, as I have explained already.
So one norm is what?
One norm is just a matrix one norm, and is the sum of singular values.
Okay.
So the trace norm.
It's not equal to trace norm. Is it? Yeah, no. Trace norm is just the squared value of singular values, I guess. This is the definition of trace norm, and the one norm is just the sum of singular values.
No, like the first is Hilbert-Schmidt, right?
Yes.
Yeah.
Oh.
Yeah, trace norm is like up to, yeah, it's one norm.
Oh, really? Okay, I'm sorry. So, yeah, this is what we want. And the proof is rather simple. We just use some standard probability theory technique that says that for any IID random variables satisfy this condition exactly equals to that condition when n is larger than this value, okay, which is sometimes called Hoyle-Ping inequality. In our algorithm, we have this one, and we have the unbiased estimator for this value, and by the Cauchy-Schwarz inequality, this is bounded from above by 1, and therefore the max norm or the estimator is bounded from just the sum of singular value for pi, and we have got this. We use a lot of standard probability theory here, and m appears here. This one just on front. Yep. So now we have the two results already explained. So now it might be a good time to talk about applications of 1 and 2. Yeah.
I have a question. Is the norm of P term kind of
Well, whichever we find here.
necessary or
Yeah. So is there any possibility that we can eliminate this for some
because
specific functions?
if you express the polynomial as using the trace of P times the unitary sum, I don't have a certain thing. Because the term could be quite big, right?
Yeah, can be.
Yes.
So I guess my question is how optimal is this?
Yeah.
Right, because it's some bound on the max, right?
Bound.
Yeah, it's just some bound on the max of this estimator, right?
Yeah, sure. Just
So like is it like how tight is it? Like,
Also, okay. But yeah, it really depends on specific functions. Some functions have a large p, then our result might not be optimal. But for some other functions, we have smaller p, then
Don't formally have a lower bound.
no, for any, for any p. That is the result related to the first one. The first one concerned with, unified framework, but this only gives algorithm. It can be efficient sometimes, but it cannot be all the time. Yep. So one application of first result is just calculation of degree. And trace function, one important example, has 1 degree, and therefore degree f is equal to 1. So this means constant number of samples suffice for the estimation under the average bias criteria. The next, the determinant is d degree by definition, just this sign of, sign of terms. Each of the term has a d degree, so it has d degree in total, and it's roughly equals to d, and therefore the d sum suffices.
So just just one question or comment. So constant number of queries, maybe not some. I'm a bit like confused, like because I'm
samples and queries almost the same term to me.
Okay, but can you go to the previous slides, like to because you're after the right. So so it just might happen that for specific polynomial, this one norm of p is large.
Yeah.
Right, and it's sort of you have degree m polynomial, but then this norm kind of can depend on m as well in some sense, right?
Sure.
So in that sense,
And we can, for one polynomial p, we may have some matrix p's.
Yeah.
Not one, not unique. Yeah, there are some other possibility, and which may have a smaller norm.
Sure. Just like if you go, it's maybe I'm confused about different node. No, just to the next slide, to the side where you had examples, right?
But this is just the example of the first result.
Yeah, okay, so you don't really care
about
whether you just care if thing is unbiased or not. So that's all you care about. Okay. Because it's
So let me get to my previous question. So is the number of samples the same as the number of shots of that algorithm?
Shots? What do you mean by
runs of your algorithm? You have this quantum circuit presenting generalized Adamar algorithm.
Yep.
You have to run it to get some results several times.
Right.
Is this the same number of runs? Is the number of runs? Does the number of runs correspond to the samples? What you call samples?
Yes, basically yes. So when you try to run the algorithm many times, we have to count each of the runs.
So this is the sample in your language.
Sample means just number of. So how many times do you need to use the control U?
But the circuit has a constant number controlled use for each run, right?
It is somehow related.
Yeah, it's not the same, because in the when computing the bias of the estimator, we don't care about the shot-to-shot variation. We only care about the expectation. We want the expectation to be close, and we don't care about the variation between shots. So the number of shots is irrelevant here. The thing that matters is how many times inside the circuit we apply the unitary.
Yeah. So for fixed circuit.
So this is for the first result.
So this is the number of unitary gates in your circuit.
Yes.
Okay. Okay.
Why do we call it sample?
It's a traditional.
No, but I think it would be good like to just distinguish, because like I was confused by the same thing,
Alright.
right? Because like sample is like when you repeat experiments, probably samples. So for this first result, it's not about samples, but it's about queries. Okay, so how many queries you need to have unbiased estimator of the quantity you are interested. And samples, like it's more natural for the PAC setting when you collect statistics.
Okay.
Because like it's very, I mean, I think many people were confused here,
Oh,
and we
sure.
work on related things, so it's not.
Oh,
Yeah.
okay.
Yeah. Okay.
So yeah, one other explanation is for fixed circuit, we may have, several unitaries, say 5 unitaries, and we may run this algorithm several times, say 6 times, then the number of samples required is 30. Okay. And this is the first result, the application. The applications for the second result is, of course, start with the trace or determinant. And it says that we can show that there exists some good polynomial that the norm, one norm is constant for trace u and also determinant. So we have to take another good polynomial for determinant. The distinct polynomial for trace of u and determinant. And therefore we can just plug 1 here, and approximately this number of samples are sufficient for trace u, and this number of samples for determinant, and which is optimal for small epsilon and delta epsilon.
Also, I have a question. Because for a given polynomial small p, you can have many matrices capital P, which correspond to the same polynomial, and right?
Yep, you're right.
And some of them might have the norm of capital P. For some of them might be bigger or smaller, right? Depending on capital P. So, is there a way of expressing the minimum over capital P in terms of properties of the initial polynomial?
I don't know. It's outside of my work.
It's kind of like the bound is there. It's kind of not intrinsic, like it doesn't depend only on the polynomial itself. It depends on the particular representation of the polynomial, right? Yeah.
So I have a just question about this trace. So, what is this good polynomial for the trace? Because previously just Hadamar's test was giving just like it was like trace 1 over D, right? Like so probably it had like overhead, like so this Hadamard test was giving bad polynomial in a sense.
Sorry. So I have missed the 1 over D here.
Okay, fine. Good. I see. So you sort of you sort of connect like so those bounds sort of match known algorithms.
Yep, in the first part, yes.
Good. Okay, but a question about epsilon now. So just naively, wouldn't it be possible to use something like amplitude amplification to evolve dependence on epsilon?
I guess it's possible, but it uses controlled inverse unitary operation.
I see. And then because you say it's optimal for small epsilon, so without inverses of you cannot.
But for small epsilon the delta, so we can just fix, meaning it's just fixed.
You mean for fixed?
Yeah,
okay,
for
so
some...
we have different. Okay, for me, small would be like depending what happens if those things go to 0. But what you mean like for constant?
Constant, yes.
Fixed, small or not constant.
Yep.
Okay, fine. Okay.
So and another example, non-trivial example, is the matrix elements of irreducible representation. And this serves as a very fundamental quantity in harmonic analysis. So it's important that some works care about the irreducible representation of some groups. And we can also show that the existence of good P that is constant for any kind of irreps. And therefore we can have this number of samples sufficient for the
irreducible, each of the irreducible representations.
It is also optimal for some small fixed epsilon that. Okay. So, yep, summary is following. In this work, we have developed some framework for estimating F, and under the average bus criterion, we can show that optimal sample complexity is roughly equals to degree of F, and we have generalized Alabama test to achieve optimal bounds, and the application includes some functions. That's it. Thank you.
Thanks, Daiki. Right. So see, it was 1 hour in total.
There were other questions, though, you know.
Yeah. Crowd. But okay, if there are questions or further questions or comments, like now there is time.
Yep. I have a question which might be a comment on the show.
Sure.
So I think a lot of the quantities that we end up caring about in quantum information are central functions on the unitary group. Like they don't care about your conjugacy class, like trace and det, or whatever. If I multiply my unitary by like v and v dagger on both sides, like it's the function of most of the quantities we care about of unitaries are central.
Oh, so you're talking
So-
about the estimation for unitary invariant function?
Yeah, something like this. So like, my question is basically, have you thought about what happens to your algorithms if I only care about central functions? Because then like all the harmonic analysis and stuff gets really easy, or easier at least, and things get nicer. The Peter-Wald theorem is a bit simpler.
Yeah. I don't know. So for the first result, I can anyway prove, of course, which can be applied to any kind of function. But the second result, I'm not sure. But yeah. Of course, there are several works I aware of that focuses on the such functions, such specific.
Someone's done it. So someone's already looked at this. for central
Yeah, but not
functions.
exactly equals to the estimation.
Okay.
Yeah, but it's somehow related to estimation, I guess.
Interesting.
Yeah.
Yeah.
Yes, thank you.
Just possibly personal bias, because I spent a decent amount of the last year thinking about like expressing central functions on the unitary group in terms of sums of characters and stuff. Yeah.
Yeah.
This is doable.
Yeah. So we can get any kind of characters for the unitary group. It becomes the cons complete orthonormal basis for central function. Yes.
Yeah, it might be some nice stuff might happen. I don't know.
Okay, other questions or comments? I mean, I have one. So, where do you want to go with this next? Like, do you have like idea like to apply this further in some context or to generalize?
I do not have any.
Okay. Okay. Yeah, I don't have like okay. Some generalizations would be like for projective unitary group, right? Different models of access are no states, right? You work in just do functions of states.
Yeah. So
possibly similar game, I guess.
if this paper has been rejected several times, I'd like to generalize this.
Okay, we are recording this. Fine.
Oh, really? Please.
Okay. Good. Okay, if there are no further questions or comments, let's thank again.
Thank you.